A warm greetings to everyone, and I Abhishek welcome back you again to second session of this day 4 of this GIAN course. So in this session, Professor Tokonami sir will continue to give his lecture in continuation to his previous lectures, and he will be delivering his talk on regulations of norms. So I invite Professor Tokonami sir to deliver his talk.
Thank you for your introduction. Can you hear me?
Yes, sir, I can hear you.
Okay. How about my slide?
Yes, sir. Your slides are visible, sir. You can make it just move.
Move?
Yes, sir.
Moving?
The slides are moving. Yes, sir.
Okay. So I have last two lectures today. The first one, I would like to talk about regulations of norm. What is norm? Norm is a naturally occurring radioactive material. Radioactive material containing no significant amount of radionuclides other than naturally occurring radionuclides. The exact definition of significant amounts would be a regulatory decision. Material in which the activity concentrations of the naturally occurring radionuclides have been changed by a process is included in naturally occurring radioactive material. Naturally occurring radioactive material or norm should be used in the singular unless difference is explicitly being made to various materials. Radioactive material is a material designated in natural law or by a regulatory body as being subject to regulatory control because of its radioactivity. This is from the IAEA safety glossary, terminology used in the nuclear safety and radiation protection. Regarding radiological properties, a total of 36 radionuclides are present in the three natural radioactive decay series: uranium-238, uranium-235, and thorium-232. Analyzing known materials requires determining which radionuclides need to be identified and quantified. The focus is primarily on long-lived radionuclides. Non-radiological aspects. Materials may contain acid-forming minerals. The solubility of the host materials should be considered. The tendency of the material to form dust is also significant. Here is a decay chain of uranium series, thorium series, and actinium series. Regarding radiological properties, focusing on long-lived alpha emitters, they are uranium series such as uranium-238, uranium-234, thorium-230, radium-226, lead-210, and polonium-210. Thorium series, thorium-232, radium-228, and thorium-228. Gamma emitters, Thalium-208, Actinium-228, Radium-226, etc., and Potassium-40. Focuses on radon, toron, and their decay products. Characterization depends on the type of material being analyzed. For unprocessed materials, the uranium and thorium decay chains are typically assumed to be in circular equilibrium, requiring an analysis of only the parent radionuclides, such as uranium and thorium. For processed materials, it is necessary to determine which radionuclides are present and their concentrations. Health hazard of norm. The main health risk of norm is cancer, as its ionizing radiation is carcinogenic. Increased exposure raises cancer risk slightly. Personnel can be exposed to radiation emitted by norm in two primary ways. First one, irradiation. Exposure occurs when radiation is emitted by materials located outside the body. Second, contamination. Due to inhalation or ingestion of material containing radionuclides, such as dust particles, we need to consider this contamination. All building materials, natural radioactivity of the building materials. All building materials contain various amounts of natural radioactive nuclides. Materials derived from rock and soil contain mainly natural radionuclides of the uranium-238 and thorium-232 series, and the radioactive isotope of potassium-40. In the uranium series, decay chain segment starting from radium-226 is radiologically the most important. Here is a typical and maximal activity concentration in common buildings, materials, and industrial byproducts used for building materials in the European Union, EU. Material, most common buildings, typical activity concentration with radium-226, thorium-232, potassium-40, and the maximum activity concentration. Concrete has 40 becquerel per kilogram, 30 thorium, 30 becquerel per kilogram, potassium-40, 400 becquerel per kilogram. As a maximum activity concentration, in the case of concrete, 240 thorium-232, 190, for potassium-40, 1,600 becquerel per kilogram. Aerated and lightweight concrete, 60 for radium-226, 40 for thorium-232, 430 for potassium-40, 2,600 becquerel per kilogram for radium-226, 190 for thorium-232, 1,600 for potassium-40. Clay bricks, as a typical value, 50 for radium-226, 50 for thorium-232, 670 for cadmium-40, potassium-40, as a maximum activity, 200 becquerel per kilogram for radium-226, 200 becquerel per kilogram for thorium-232, and 2,000 becquerel per kilogram for potassium-40. Sand-lime bricks. This is lower than other common other building materials. 10 becquerel per kilogram for radium-226, thorium 10 becquerel per kilogram, 330 for potassium-40. Even as maximum activity, (25 becquerel per kilogram as radium-226, thorium 30, and potassium-40, 700. Natural building stones, 60 radium-226, 60 thorium-232, 640 for potassium-40. As maximum activity, in the case of natural building stones, 500 for radium, 310 for thorium, and 4,000 for potassium. In the case of natural gypsum, the activity is relatively low. It is comparable to sand-lime bricks, 10 for radium, 10 for thorium, and 80 for potassium-40. As maximum activity, 70 for radium, 100 for thorium, and 200 for potassium. Common industrial byproduct used in building materials. Byproduct gypsum, phosphogypsum, as you can see, the radium contents, radium activity is much higher than others, which are concentrated 390 becquerel per kilogram for radium-226. In the case of thorium, 20, the potassium 60, as a maximum 1,100. In the case of thorium, 160, the potassium-40, 300. Blast furnace slag, 270 for radium-226, 70 becquerel per kilogram for thorium-232, and 240 for potassium-40 as a typical activity. As maximum activity, 2,100 for radium-226, 340 for thorium-232, 1,000 becquerel per kilogram for potassium-40. Coal fly ash, as a typical value, 180 for radium, 100 thorium, for thorium and 650 for potassium, 1100 for radium, 300 for thorium, 1500 for potassium 40 as a minimum activity concentration in becquerel per kilogram. Here are examples of the annual effective dose due to external exposure. First, we classified into 4 categories: low activity material, average concrete, upper level of normality, and enhanced concentrations. In this low activity materials, 10 becquerel per kilogram of radium, 10 becquerel per kilogram of thorium-232, 300 becquerel per kilogram of potassium 40. When we calculate the annual excess dose based on structures in a building causing the irradiation, floor, ceiling, and walls, all structures, it contains these radioactivities. The level is less than background dose, floor and walls, namely wooden ceiling, floors only, that is wooden house with concrete floor. Both are less than background dose. At average concrete, average value, in this case, floor, ceiling, and walls contains this radioactivity. It gives 0.25 millisievert per year. Floor and walls, 0.1 millisievert. Floor only, less than background dose. If we take radioactivities with these values, when we calculate annual excess dose, floor, ceiling, and walls gives 1.1 millisievert. Floor and walls gives 0.74 millisievert. Floor only is 0.11 millisievert. Finally, enhanced concentration at the maximum radioactivity. With these values, the annual excess dose was calculated to be like this. Floor, ceiling, walls, 2.3 millisievert per year. Floors, walls, 1.6 millisievert. Floor only, 0.41 millisievert. Parameters values used in calculating the dose. Here is a table for the calculation, dose calculation. Dimension of the model room, 4 meters by 5 meters by 2.8 meters. Thickness and density of the structures, to 20 centimeters to 1,350 kilogram per square cubic meter. Annual exposure time, 7,000 hours. Dose conversion is given as 0.7 millisievert per gray. Background 50 nanogray per hour. Specific dose rate, nanogray per hour per becquerel per kilogram. Look at here. Structure of the inner building causing the irradiation. Floor, ceiling, and walls, 0.92 nanogray per hour. 1.1 nanogram per hour per becquerel per kilogram, like this. Fluors only 0.24 for radium, nanogram per hour per becquerel per kilogram. .28 for thorium-232, nanogram per hour per becquerel per kilogram, 0.02 nanogram per hour per becquerel per kilogram. Superficial material, tiles or stones on the walls, thickness of 3 centimeters and densities 2,600 kilogram per cubic meter. 0.12 for radium, 0.14 for thorium-232, and 0.0096 for potassium-40. I'm talking about building materials and radon. The internal exposure is caused by the inhalation of radon, thorium, and their short-lived progeny. Radon is part of the radioactive decay series of uranium, which is present in building materials. Because radon is inert gas, it can move rather freely through porous media, such as building materials. The most important source of indoor radon is the underlying soil, but in some cases, the building materials may be an important source. In most cases, the main part of indoor radon on the upper floors of a building originate from building materials. Typical excess indoor radon concentration due to building materials is about 10 to 20 becquerel per cubic meter in some regions, in some zones, and in rare cases, it may rise up to greater than 1,000 becquerel per cubic meter. Wait a moment. Radiation protection principles. The purpose of setting controls on the radioactive building materials is to limit the radiation exposure due to materials with enhanced or elevated levels of natural radionuclides. The dose to the general public should be kept as low as reasonably achievable, ALARA. Since small from building materials are ubiquitous, controls should be based on exposure levels which are above. Above typical levels of exposures and their normal situations. Okay, wait a moment. I have to change. Sorry. Okay. Well, since of small exposure from building materials ubiquitous control should be based on exposure levels which are above typical levels of exposures and their normal situations. All buildings contain some natural radioactivity. Small unavoidable exposures need to be exempted from all possible controls. Restricting the use of certain building materials might have significant economical, environmental, or social consequences locally and nationally. Such consequences, together with the national levels of radioactivity in building materials, should be assessed and considered when establishing binding regulations. The amount of radium in building materials should be restricted at least to a level where it is unlikely that it could be a major source for exceeding the design of level for indoor radon introduced in the Commission recommendation with 200 becquerel per kilometer. Regarding controls on the radioactivity of building materials, based on the following radiological criteria and principles, those criterion for controls should be based on a dose criterion which is established considering overall national circumstances. Controls can be based on a lower dose criterion if it is judged that this is desirable and will not lead to impractical controls. It is recommended that the controls should be based on a dose in the range of 0.3 to 1 millisievert per year. Note that this is the excess gamma dose to that received outdoors. As exemption level, building materials should be exempt from all restrictions concerning their radioactivity if the excess gamma radiation originating from them increases the annual effective dose of a member of the public by 0.3 millisievert at the most. Note that this is the excess gamma dose to that received outdoors. Separate limitation for radon or thoron exhaling from building materials should be considered where previous evaluations show that building materials may be a significant source of indoor radon or thoron. Here are the investigation levels for practical monitoring purposes. It is practical to present investigation levels in the form of an activity concentration index. You can see this formula. The activity concentration index should take into account typical rates and amounts in which the material is used in a building. The following activity concentration index is derived for identifying whether a dose criterion is met. Dose criterion here, materials used in bulk amounts, such as concrete, superficial and other materials with restricted use, such as tiles, boards, etc. Dose criterion is when the dose criterion is 0.3 millisievert per year. index is less than 0.5. Criterion of 1 millisievert per year, index should be less than 1. In the case of superficial and other materials with restricted use, in the case of 0.3 millisievert per year, I index less than 2. In the case of 1 millisievert per year, index should be less than 6. How is the index derived? The activity index is derived to indicate whether the annual dose due to the excess external gamma radiation in a building may exceed 1 millisievert. The activity index is calculated like this. Factor for radium dose criterion 1 millisievert per year equals sievert per 10 to minus 3 minus third, and calculated. The factor for thorium, the radium is eventually concentration will be 276 becquerel per kilogram. Then after rounded value is 300 becquerel per kilogram. Factor for thorium. Criterion 1 millisievert per year is thorium 232 concentration is here, and eventually thorium concentration will be 231 becquerel per kilogram. The rounded value is 200 becquerel per kilogram. Here's a potassium. This is wrong. Potassium body, the same manner as previous two equations. The potassium 40 concentration will be 3,176 becquerel per kilogram. Rounded value 300 becquerel per kilogram. So the index can be written like this. Here is a 0.92, 1.1, and 0.08 are coming from this one. Specific dose rate, coefficient. Here is important information. The activity concentration index should be used only as a screening tool for identifying materials which might be of concern. Any actual decision on restricting the use of a material should be based on a separate dose assessment. Such assessment should be based on scenarios where the material is used in a typical way for the type of material in question. Scenarios resulting in theoretical, mostly unlikely maximal doses should be avoided. Here is a flowchart of the recommended system of control of building materials. First, determine activity concentration of radionuclides in the building materials. Then, determine the activity index. If the index is less than 1 or 6, no restrictions. If not, first assess the dose. If the dose is less than reference level, namely 1 millisievert, that you we don't have to do anything, no restrictions. If not, dose is more than reference level of 1 millisievert. Decide on appropriate measures. This slide shows the gamma radiation from building material. Sorry. Gamma radiation from building materials in existing building materials. Buildings. Protective actions may be necessary for existing buildings with high annual effective dose levels caused by gamma radiation due to radionuclides in the building materials. If considered necessary, the national authority should establish different levels for exposure to gamma radiation emitted from building materials in existing buildings. Feasible protective measures are not easy to implement. The national authority should consider requiring protective actions to be mandatory for existing buildings of high occupancy where the effective dose levels exceed 100 millisievert. Note that the protective measure carries serious economic and penalties and should not be applied without careful consideration. Here's the role of building material as an indoor radon source. How does radon release from building materials? This is a feature of radon. Feature on radon comes from soil and rocks and building materials. Here is a equation of the acceleration rate. This is the diffusion length. Effective diffusion coefficient is dominated by transport, which is an important parameter for transport and emanated radon. Radium decay, emanation, the diffusion, and acceleration from surface to the atmosphere. Here is the emanation coefficient, F, is dimensionless. The ratio between the escape radon into pore space to the total amount of generated radon. Radon is generated from radium in soil, rocks, and building materials. Therefore, radium concentration is important. Here's the equation reported in ANSCA 2000. Radon acceleration rate from the soil surface is written by this equation. Radium-226 concentration, decay constant of radon-222, emanation coefficient, density of the soil, and the porosity of the soil, and diffusion length. There are important parameters to determine the acceleration rate. This table shows different materials and emanation coefficient and diffusion length. Concrete, 0.1 to 0.4, the emanation coefficient, 0.06 to 0.2 as diffusion length. Brick, 0.02 to 0.1 emanation coefficient 0.2 to 0.4. Gypsum 0.03 to 0.2. 0.8 to 1.3 as diffusion length. Cement. The emanation coefficient is quite small compared to other three, especially other concrete. Cement 0.02 to 0.05. No data on diffusion length. Fly ash also much smaller than others. Then this is a typical exhalation rate from various building materials. In the case of concrete, 2 to 30 becquerel per square meter per hour. The surface radon exhalation rate. Byproduct gypsum 5 to 40. Aram shell concrete 50 to 200. Lightweight concrete 1 to 3. Brick 2 to 5. Here is a table on the various materials and mass exhalation rate expressed in becquerel per kilogram per hour. The concrete 0.002 to 0.1. The brick 0.001 to 0.05. Aram shell concrete 2 to 3. Natural gypsum 0.002 to 0.02. This slide describes the contribution to indoor radon concentration from different building materials. Using this formula, this is C, radon concentration, E, exhalation rate per unit area, surface exhalation rate, and S, exhaling area. B, room volume. Lambda V is air exchange rate, ventilation rate of the room. Here are the various materials. Concrete, we assume the exhalation rate of 10 becquerel per square meter per hour. The maximum radon concentration will be 40 becquerel per meter. Realistic value 20. Lightweight concrete, when we assume the acceleration rate of 2, the radon concentration will be 7 as maximum, 4 as realistic value. Aram shell concrete, if we assume the acceleration rate of 200 becquerel per square meter per hour, the radon concentration goes up to 700 becquerel per meter, and realistic value is 400 becquerel per meter. Clay brick, when we assume the acceleration rate of 4 becquerel per square meter per hour, the radon concentration will be 15 becquerel per meter as maximum and 5 becquerel per meter as a realistic value. Byproduct gypsum, when we assume the acceleration rate 20 becquerel per square meter per hour, the radon concentration will be 70 as maximum, 10 as realistic value. This slide exemplifies the experimental setup for mass exhalation rate measurement. So in our laboratory, we use a scintillation cell. we placed the building materials in the chamber, accumulation chamber here. And we took the samples, air samples, to situation cell and measure the radon concentration. There is an equation to determine that this is a F means a emanation coefficient. AE, the radon concentration in equilibrium condition. A, radium concentration in building materials. Volume is accumulation chamber, and W, mass of sample. I will show some data, natural radioactivity concentrations at industry sectors. Petroleum, oil and gas here. Produced water, the radium-226, 612 becquerel per gram. Becquerel per kilogram, and scale 611 for both radium-226 and radium-228. In the mineral processing, the highest value gives with a discard byproduct. In the case of radium-226, it's 3,130 becquerel per kilogram. Radium-228, 8,460 becquerel per kilogram. In the case of water treatment, sediment is the highest, maybe the highest. But compared to other materials, other activity, it's not so high. Radium-226, the 64 becquerel per kilogram. Radium-228, 108. And here is a mineral dressing, zircon and tantalum. Yeah. In the case of zircon, it's much higher than other material. Phosphate production, phosphogypsum gives a high radioactivity of radium-226, 750 becquerel per kilogram. Oil and natural gas production. During the extraction of oil and natural gas, the natural radionuclides from underground formations are brought to the surface. Elevated activity to radium present in NOM are often released by oil and gas industry, particularly in production waters. During the extraction process, radium is precipitated along with barium and strontium. A portion of the radium is deposited during the scale formation process, and other portion is discharged to the sea with effluent ends. The most important radionuclides in scales and other participants are the isotopes of radium with specific activity ranging from 100 to 1000 becquerel per kilogram. concentrations of lead-210 and polonium-210 in sludge and scales can vary between 20 and 1,000 becquerel per kilogram. The disposal of scale from oil extraction industry installation and of sludge containing known can be of environmental significance, with contamination of land being the major concern. For example, the average radium concentrations in soils sampled at an oil field contaminated with known on western Kentucky, United States, were 32,560 becquerel per kilogram. Bauxite and aluminum industry. Bauxite is used to produce alumina, which is then used to produce aluminum. Waste can be generated at several points in the production process. Bauxite ores sometimes contain elevated concentrations of natural uranium and thorium. Volume is reduced by half, but majority of radionuclides report to mud. Mud contains radionuclide concentrations above background levels. Internationally, only about 2 to 3% of bauxite residuals are reduced in a productive way. Phosphate industry. Phosphate rocks is used extensively, firstly as a source of phosphorus for fertilizers and secondly for making phosphoric acid and gypsum. Ores typically contain about 1,500 becquerel per kilogram of uranium and radium. The fertilizers become somewhat enriched in uranium up to 150% relative to the ore, while 80% of radium, 30% of thorium-232, and 5% of uranium are left in the phosphogypsum. Phosphate industry. The use of phosphate fertilizers in agriculture and of gypsum in building materials is a further source of possible exposure of the public. Elevated radon exposure of the public can further be expected in sites being developed for housing. The sludge, which contains radium-226 concentrations ranging from 750 to 1,100 becquerel per kilogram, has been used as building material in the United States, especially communities in southeast Idaho. Coal mines and processing. The average specific activity of both uranium-238 and thorium-232 in coal is generally around 20 becquerel per kilogram, ranging from 5 to 300 becquerel per kilogram. During the burning of coal, the organic compounds are converted into gases, while the inorganic elements, which include the significant naturally occurring radionuclides, are concentrated in the ashes. In general, the radionuclide enhancement factor in ash is about 10. Leaching from fly ash is low, and therefore there are few restrictions on the use of fly ash in landfill and road construction. The use of fly ash for building construction results in radiation exposure from both direct irradiation and radon exhalation. Dumping fly ash may increase the radiation level around the dump site. The most significant exposure pathways are ingestion and inhalation of the isotopes lead-210 and polonium-210. Building industry, extensive use of non-reduce fly ash produced in large quantities from coal burning, sludges of steel works and metal recycling industries, phosphogypsum, red mud of the aluminum processing industry. Extensive use of non-residue fly ash produced in large quantities from coal burning, sludges of steel works and metal recycling industries, phosphogypsum, red mud of aluminum processing industry. None in materials is source of gamma radiation. Radon exhalation also the potential source of exposure. Exposure scenarios, longer times are necessary. Rare earth and titanium oxide industries. Lantanoid rare earth metals has 6 elements. Bastnasite and monazite are the most important minerals containing rare earth metals. Activity concentration of bastnasite 900 to 1,200 becquerel per kilogram for uranium-238 decay series, 700 to 7,000 becquerel per kilogram for thorium-232 decay series. Activity concentration of monazite, as you know, 10,000, much higher, 10,000 to 50,000 becquerel per kilogram for uranium decay series, 5,000 to 350,000 becquerel per kilogram for thorium-232 decay series. Rare earth titanium oxide industries. Activity concentration of titanium or 300 to 600 becquerel per kilogram for uranium-238 series, 35 to 600 becquerel per kilogram for thorium-232 decay series. For titanium production, specific activities of radium sulfate participate in pigments or scales may be as high as 400,000 becquerel per kilogram, and thorium-228 levels may be higher than 1 times 10 to 6 becquerel per kilogram. Exposure pathways include external irradiation and immigration of radionuclides from landfill. Here is an example of the measurement at rare earth extraction plant in Thailand. Actually, we made this measurement in the rare earth extraction plant. High gamma dose rate was observed at Department of Waste Management. The value is 6.3 microgray per hour. The average gamma dose rate was 0.43 microgray per hour. Average gamma dose rate nearby the plant, around the plant, is this normal level, 22 nanogray per hour. High radon and thorium concentration were observed, but uranium radon levels more than 400 becquerel per cubic meter, and thorium concentration more than 5,000 becquerel per cubic meter. Professor Mehra, may I have a short break?
Hello.
Hello, may I have a short break?
Sir, not able to hear you.
Excuse me?
Yes, sir.
Yeah.
So, dear participants, if you have any question, you may unmute yourself and ask a question. So, in case participants do not have any question, we will be taking a break of 10 minutes, and we will be joining the meet again to resume the session at 2:40 p.m.
Okay.
So after 10 minutes, we will resume the session.
Okay. All right.
Yeah, yes, sir.